Anyway, what is Nix? Nix is a functional programming language and package manager. So the output of a Nix program is basically what determines what packages and configurations are installed to your system. So if your program says, I want to have Firefox installed, then it will install Firefox. Stuff like that. So all the dependencies are stored independently in this thing that they call the Nix store, and then they're linked to be used in the currently running system. I'm going to zoom out very slightly just so that this fits onto the screen. That's a little bit better. Cool. So after you build and you store all of those packages, every package uses its own set of dependencies. So that means it's impossible to end up in dependency hell. Has anyone experienced that thing where you want to install one program, but then it depends on some other program, but then another program depends on a different version of that other program? Really, really horrible. Doesn't happen in NixOS, because what happens is that every single package has its own set of dependencies. So for example, in the course Comp 2511, they made the questionable life choice of using Java 17. Anyway, the problem is that JDTLS, which is the language server that gives you nice editor support for Java, it requires Java 21. So what that means is if I want to use Java 17, I can't have the language server set up easily, right? That really sucks. Not on Nix, because what I can do is I can say, yeah, environment system packages, I want JDK 17. That's going to give me Java version 17. Then I just say, I want JDT language server, which is the language server, and it will have its own personal copy of Java 21 that is perfectly linked to only this program. As such, it won't conflict with this. That is very, very cool. However, it gets even better. So NixOS is basically, what if we turned that into an entire operating system? So every single package on the system, every core system configuration, so like users, file systems, mount points, all that stuff, it's all configured in this one Nix programming language. So there's no more need to learn random commands or edit random files, or at least in theory. And you can set up basically everything from a single configuration. And if anything breaks, you go and you roll back to the previous working version and you've got a working system again. That's really cool. So you can see here, like, I've still got my old Fedora installed on another SSD. I can just say, hey, mount it to /media/isma. This is the disk to mount, and the file system is ButterFS. And then I don't need to remember how to edit an fstab. It's going to generate the fstab for me. That's really, really cool. Or I can set my computer's name, or set the time zone to Sydney, or create my user. Like, who knows how to create a user on Linux? I certainly don't. However, single thing, and I never have to remember how to do it again because it's just stored inside my configuration file, which is conveniently synced to a Git repository. Pretty nice, right? So what is NixOS up against? So the two tools that I'm going to compare it to today are Mies, which is a development package and tool management system. It's basically a single tool that installs and manages all of your development tools. It's pretty cool. We'll talk about it later. Then there's also Docker, which is a way to create consistent and easily deployable builds of software so that you get an isolated development environment or a production environment or a building environment. But how do they compare? There is only one way to find out, and so I switched to NixOS. Anyway, basically, for this little experiment, I tried to use the NixOS way of doing things whenever I possibly could. So whenever there was some kind of tool that I already knew of to solve a problem, I would avoid it if NixOS claimed to be able to do that thing well. So basically, I kept Fedora installed just in case because I can't be without a system. If my system's broken, then I am out of a job. But yeah, I avoided booting into it, and I think I only needed it once throughout the entire 2 weeks, which is pretty impressive. So I used it for tutoring work, so running tutorials with my little slides program, doing marking, that sort of thing, working on my personal programming projects, and playing a couple of games. I only really got around to doing that last night, but it was pretty fun. We'll talk about it later. So what was it like? Not great. So first things first, while the popular packages are cached, a lot of software ends up getting built from source. And I don't know about you guys, compiling software takes a while. I made the mistake of trying to install CUDA without realizing it would be installed from source. CUDA being a thing that NVIDIA makes to do calculations on the GPU. Very cool. After 45 minutes of using 100% of every single CPU core and being basically unable to use my system, I had to give up and cancel it. It said it was up to 3% compilation. It was terrifying. I had to stop it. Horrible experience. And even when you make literally 0 changes to your configuration, a rebuild still takes about 20 seconds. That's especially annoying because there's pretty subpar editor support for Nix. Like with most languages, you put your mouse over something and you'll get documentation about it and it's great. Not with Nix because it is a dynamically typed language, meaning that the editor support is making a lot of guesses about what the types of all the different pieces of data are, and as such, it can't give you nearly as much useful information about them. As such, most of the mistakes that I made while trying to configure it were only detected while I tried to build my system rather than as I typed, which really, really slowed down the speed that I could iterate on things. Also, the documentation was a nightmare. There are 2 different wikis for some reason. I don't know why this is the case. And then even then, half the time the wikis don't work, so you'll be scouring forum posts. And then sometimes you'll be going and literally reading the NixOS source code to try and figure out how to do something. Horrible, horrible documentation. And the moment I wanted to do anything non-trivial, I would quickly run into issues and I would be sent on a Google hunt. Literally, so many times I would be Googling, how do I do this? And it would be really, really frustrating because on most other systems, once you know the system, most things are pretty easy to set up. NixOS didn't have that level of consistency for me, and I was a little bit disappointed by that. Also, we need to talk about the jank. So there are a bunch of just random bugs and glitches that I experienced that were really annoying. So like, sometimes when I open an app, instead of getting the application icon, I would get this generic executable icon. I'll show you what I mean quickly. I've got a little tool here called Make MKV, which is what I use for doing my physical media library stuff. I'll open that up, and you saw the icon there. It's different to the icon here, and it says unknown. I don't know why this is the case, but it's really annoying. And also, sometimes my laptop's currently connected to Wi-Fi, so I can't show you right now. But like sometimes when it's not connected to the internet, it'll be like, yeah, you've got an Ethernet connection. No, I don't. My laptop doesn't have an Ethernet port. Occasionally also, after I would do a rebuild, all of my apps would disappear from the launcher, making me think that I accidentally deleted everything. Terrifying. However, when things did work, they worked consistently. Once I got a working configuration, I never experienced a thing where something that I thought would continue to work would break. In fact, some apps were even more stable than they were on Fedora, like they would crash slightly less or they would have fewer random issues. But let's get into some more specific uses. So first of all, what's it like for programming? So one of the really annoying things I found is that it is impossible to install multiple versions of a tool side by side. So in Comp 1531, we use Node version 20. However, for some of my projects, because I'm sick of using a 5-year-old version of Node, I'm not sure if it's actually 5 years old, but like it's multiple years old, and I want to use a newer version like Node 22 or 24. Can't install them side by side, really annoying. Also, for interpreted languages, everything except for the binary dependencies works fine. But for other languages, when you have binary dependencies, unless you install them install those things and build them specifically using Nix's infrastructure, they just don't work nicely. You'll get random errors. Like, there are some ways to fix it, but they just didn't work all that reliably. So as such, what you need to do is for every project that has non-trivial dependencies, you need to go and you need to manually configure it by creating this thing called a Nix dev shell, which is, if anyone knows Python virtual environments, they're the equivalent of that, except instead of only having isolated Python packages, they have an isolated version of all the packages you need, which is a really cool concept, but they're really tedious to set up. Like, check out this dev shell configuration. This is the slideshow viewer I'm using, Slides XP. It's a super janky thing I made myself. And to get it working on NixOS, check out this wonderful code here. Yeah. So that isn't all either, because in order to get it working, I needed to create a wrapper package, because you can't just wrap a package that hasn't been nixed unless you fork its source code, which is really annoying. So I need to write this Python code saying, print, I need this to be here, otherwise it fails to build, because otherwise it would fail to build. Insanity, right? But yeah, if you need to add one of those sorts of things, those configurations to every single repo that you work on, it's a ton of work, especially if you have many, many side projects like me. So that was kind of annoying. But yeah, different topic. What was NixOS like for gaming? Random Splotch was brought to you by GNOME. Yeah, it was so annoying. I tried to play Portal 2, and I just had these things blocking my view. It was absolutely horrible. However, that's probably GNOME's fault because GNOME is notoriously bad for gaming. So what I did was I'm like, hey, enable the GameScope session and enable GameScope. And then what that means is now from my login screen, I get a login directly into Steam. And then I effectively have my own version of SteamOS on my system with 2 lines of configuration. And for a point of comparison, I looked up how to do this on Fedora, and I didn't do this on Fedora specifically because setting this up is such a nightmare. You need to edit so many configuration files, install so many arbitrary packages. It's really, really annoying. 2 lines of code, and it literally just worked perfectly. Like, literally no issues. It was great. So the one problem was that I forgot to add GPU support. So like, no wonder all of my games were running badly. So I was just about to enable all the features by hand, and I discovered NixOS has a hardware configuration repository where for basically any pre-made device you can think of, they've got an existing hardware configuration for it, and you just need to go builtins.fetchgit and download the Git repository and say, yeah, get the Dell XPS 159500 with NVIDIA drivers. And I did that, and everything worked. And that was exceptionally cool. Like, no need to configure things by hand. In fact, I'm pretty sure that this configuration even has bug fixes for specific issues that my laptop has. Like, there was a comment there saying, we need to change this setting because the Bluetooth module for your laptop is crap, and unless you change this setting, it won't work reliably. So I presume I have more reliable Bluetooth because of this configuration that I would have otherwise never known about. That's really cool. But also, the one problem is that now whenever I want to run a game with a GPU, I need to like modify the launch options in Steam to say NVIDIA offload and then whatever the run command is. Why doesn't that work automatically? Who knows? I also couldn't figure out how to make Steam just detect the GPU by itself. But also, to be fair, I couldn't get that working in Fedora either, so like, I won't judge too hard. But next question is, what is a flake? So basically, a flake, you know how I complained about how NixOS was really slow to rebuild? Flakes are supposedly the solution for that. So like a package lock.json in Node, it stores all of the resolved dependencies, meaning that they don't need to be recalculated every time. Sounds great, right? Wrong. Anyway, I managed to completely break my system by trying and presumably failing to convert my configuration to a flake. Like, I couldn't even run the NixOS rebuild command, which is like the one thing that needs to work. So like, I tried running it, and you can't really read that error, but it's saying, error file NixOS config was not found. That's a system file. I don't know how I managed to get it so broken. Thankfully, NixOS to the rescue. All I needed to do was find all of my previous generations, because every time you rebuild your system, it stores the old version, and all I had to do was reboot into the known good configuration and go from there. So you can see, like, if I had that as my current version, then I can go from one funny number to another funny number, and I will have a working configuration, and it'll be great, right? That was really, really nice, because as much as it would be better if it didn't ruin my system, it's nice that it was able to kind of save me from itself. Anyway, attempt 2, what I tried doing was instead keeping my main configuration as a regular file and then using flakes for other parts. So for example, in 2511, they use Gradle 8.8. That's pretty old. The reason they need it is because of the terrible CSE systems, which are running like an ancient version of Debian that can't run anything newer. Problem being, accessing that is really, really painful. Like, I had to go and find this random, it goes off the end of the screen, but that's a commit hash, and that's the specific commit within the package repository that contains Gradle 8.8. And as such, like, it's neat that I'm able to do this and I was able to get it working, but not all that pleasant. But at least I could keep it isolated from everything else, as opposed to having to have that throughout the rest of my code. Anyway, how else are they useful? We can flakify comp1511's DCC compiler. It has some pretty tough requirements, but in the interest of time, I'm probably going to speed over those because I'm taking way longer than I did when I did a practice run. Anyway, so it has many, many build dependencies. Some of those are runtime dependencies, and we don't want to pollute our runtime environment with those dependencies if we can help it. But we do need to provide some compiled runtime dependencies because, like, in order to run anything compiled with DCC, you need GDB to be installed, that sort of thing. Anyway, it was pretty easy. Like, I just say, yeah, grab the dependencies from v25.05, build it for all these systems. Then down here, here's all the build time dependencies. Somewhere here, yeah, here are the runtime dependencies. I just need to copy them into the environment so that they're available. Then here are the compile time dependencies. And then it all just works, and I have a working version of DCC with a single configuration. And even better, because that's like now on GitHub now, anyone who goes and uses this particular thing as a flake, they're going to get a fully configured working DCC directly in their system with no setup required on their part. Compared to most alternatives, that's pretty nice. There's just one problem, which is that you have literally no other options, or at least no other good options. Like, hypothetically, you can run arbitrary executables by setting programs.nixld.enable equals true, and that's supposed to allow binaries to arbitrarily link to other libraries and other dependencies. However, I found it was pretty unreliable. Like, half the time it just wouldn't work, especially if there was a library or program wanted and I couldn't figure out how to install it and make it available on NixOS. That was really, really annoying. So basically, to have any non-Nixed program in your Nixed configuration, you will have to Nix it yourself. No wonder the package ecosystem for NixOS is so huge, because like, by the time you've installed something on your system, you've basically created an entire package for it, and at that point, you may as well share it with others, right? So, yeah, interesting. So let's talk about one alternative, mise en place, which is, it advertises itself as the front end to your dev end. Kind of fun, sort of almost rhymes. So what it does is it does weak isolation based on a shell script that modifies your path variable as you CD about your system, which feels super hacky, but you'd be surprised how well it works. So what does a mise configuration look like? Let's get Gradle 8.8 and a few other things. Gradle 8.8, Gradle equals 8.8. So easy. That's 17 lines shorter, and I didn't have to find this random ass commit hash to end up with the right version. Anything from npm :tsx, and I get the latest version, works for things written in Python, Ruby, Go, Rust, and more languages as well. That's really cool. What about a random binary from GitHub releases? Works as well. That's so cool. So what I love about Mise, it's so easy to use, everything just works, and it works on all systems with very little setup, and it automatically changes versions of packages depending on your current system. So if I'm in a project that needs node 22, I CD there, and node version will be 22. Then I CD back out, and I'll be back to the default version that I normally use as soon as I've CD'd out of it. That's really cool. In fact, I couldn't do a talk on that because I'd be done in 30 seconds because it's so easy. What I don't like so much about it is that not everything is handled by the existing integrations. And if you've got a tool that you want to install that has complex dependencies, you're going to find yourself writing Lua. And that's somehow even worse than what you would have to do with Nix. The other alternative is Docker, which is basically isolation via lightweight virtual machines. Probably way higher reproducibility than Mise, and might even be better than NixOS, at least if you're not using flakes, because you're literally running the same virtual machine. All of your VMs are isolated, which is good for security, and you can use it to spin up development environments and things like VS Code's remote server tools. And let's see what a Dockerized program looks like. Oh. It's not good. And the reason it's not good is because it's so imperative. It's the same as what we were dealing with back in the days of me using Fedora Linux like a week and a half ago. Like, I don't say this is what I want and it figures out the rest. Instead, I have to say this is how to get there, which is way more complicated. The build times are even slower than Nix, and it's way less secure by default, at least in terms of using it as opposed to running things within it, because being in the Docker group effectively makes you root. It's also harder to learn because you're running a full virtualized OS. You need to learn that operating system as well as learning Docker. Really, really annoying. It's also very slow to start and stop, which makes it a pain for development. The things that are okay with it is that it's used everywhere, and that if you need something, it's probably already using Docker, so you're not going to have to do stuff yourself. And once things are Dockerized, it's really easy to run them with Docker Compose, which makes them really, really, really good for running stuff on a server. But yeah, do you need NixOS? Well, you might not, but also you might. So if you just want an easy setup of development tools, use Mise instead. It's way nicer for development tools. If you're running a server, just use Docker. There are Docker images for everything, so it'll be easy. And if you want to understand the state of your system without hunting through random config files and running random commands, NixOS is incredible. So while it didn't just work like I had hoped, it worked more often than it didn't, and I was able to configure some really advanced things which would have been really painful on other systems. So I was much more impressed with NixOS than I thought that I would be. And so the question is, now do I need NixOS? So now that my self-imposed challenge is over, I'm not bound to my arbitrary all nixable things must be nixed rules. And as such, there is nothing stopping me from using a combination of the previous things. I can't live without Mies. I love the fact that I can CD and it will automatically activate the right tools for me. That's great. Thankfully, adding it to NixOS is a single line of configuration. So I did that and it all just worked. So as such, my plans are I'm going to use NixOS for my general system, Mies for management of development tools, Docker for deploying my software on my server, and for files management, I'm not sure yet. Home Manager looks interesting, but also looks slow, so I'm going to have to keep looking. But yeah, as such, my conclusion is that there are no gods of purity watching over us, despite what the NixOS wiki may have you believe. As such, you should do what makes you happy and don't stress about making things perfect, because things being perfect will not make you happy. Instead, trying new things will, even if you originally thought that you didn't need them. Who knows? Maybe you might just prove yourself wrong. Thank you very much. And also, I've got a couple of credits here. These were all the resources that I used, the various wikis, a bunch of discourse posts, a bunch of other things as well. But yeah, thank you very much. If we have time, we might do Q&A, but also I think we're 5 minutes over.
We've got time. We've got time. We've got time for questions.
Very cool.
Does anyone have a question? Max.
So you said you set up a flake or something for DCC.
Yes.
What's stopping you from contributing that upstream to Nix packages? Like, could you just send it up there?
I believe I could. They probably have higher code quality standards than I do, though.
No, no, they don't. Can confirm.
Who knows then? I did create a merge request for like the comp 1511 version of DCC saying, here's a flake that you can add if you want. But that being said, they haven't updated that thing in 2 years, so like maybe they probably won't merge it. This is also true. It's a very, very point. I went in being like, yeah, let's turn DCC into a flake, specifically because I was like, this will be a challenge as opposed to this will be useful for other people. Because you are absolutely right. No people taking comp 1511 are ever going to want to use NixOS. This is also true. More questions? Yeah?
So on the CUDA thing, I don't want to say definitively a skill issue, but I do know it's a known thing that like it's like a really difficult config option to find. That's a bit of a rite of passage for Nix users.
Okay.
But on that,
it probably is a skill issue.
On that, right? You mentioned the wiki. There being 2 wikis, things being really confusing. Mm-hmm. Do you think a portion of what makes it so difficult is the fact that the language is so kind of undocumented, and in that, what do you think of the kind of GNU alternative of GUI? Have you looked into that much?
GUI being like the GNU one?
Yeah.
I've looked into that and I was immediately turned off by the use of, what's that horrible language they use?
Heresy.
Pardon?
Heresy. Scheme.
They use Scheme, and I saw that and I was like, this looks way more scary. Because Nix, as much as it's a very strange language, it does look similar enough to JSON that if you're just doing configuration without if statements or anything, it is pretty nice to work with. The same cannot be said of Scheme, and as such, I haven't really looked into it. But yeah, a lot of the mistakes that I had were probably skill issues. However, they are skill issues that other people would also experience if they tried the same thing as me. And as such, as much as yes, the answer is that I'm stupid, the answer is also that everyone else is also stupid. And as such, NixOS should be written in such a way and documented in such a way so that even a stupid person can use it. Sound good? More questions?
All right, so I think that's it.
Thank you very, very much.
All right. Max up next. Just give me a moment.
Yes.
A moment.
That was very, very fun. Thank you. Yes. It's not that it worked automatically. It's just that you configured it before I did.
All right. But no, I need to put this in before I do this. I need to read through that.
Did I lose screen sharing halfway through that?
No, it was fun.
Okay, cool.
Yeah,
Because I appear to have lost screen sharing at this point.
Well, that's awesome.
Well, I mean, you did unplug the computer from the display.
Okay, that might have been the cause.
So you no longer have.
It all worked when it.
Yeah, but it was using like duplicate the displays, so I would have thought it would have assisted. Maybe it just didn't handle like the change of resolutions nicely.
Alright, that's connected. I need
I
a
have
new,
you.
but it doesn't have the display.
What? What do you mean?
Only one of these work. I don't remember which. Is it that one?
Oh, you have like the giant price.
Oh no, I'm gonna have to. I'm gonna have to like get a Wii remote for my tutorials and stuff.
Yes, yes.
Like that was so much more fun than I thought it would be. And I thought it was gonna be fun too.
Yes, it works. It
Which
worked yesterday.
USB-C port?
Don't remember. Maybe it's this one.
Oh, one of them works.
Yes, one of them will work.
Yeah, I think it was that one.
It's gonna work.
It's gonna work.
We're getting
Oh, this
MacBook. Do we have the right thing there? Can I?
Do you want to try?
You think that's what we need? Well, it's working.
Oh, then the browser thing's not working.
Yeah, that's expected. That's fine. That's fine.
When next? Yeah.
Laptop.
Do you want to try with HDMI?
I don't have.
I have a.
If you got a
I have
DAC, yeah. I know this at some point.
I have two. I have one that has HDMI, one that has HDMI. One that has the other. We can do this one.
It's a low bar to clear.
It's just gonna turn into another Zig. Please no.
That's new. The screen's black now. Perfect. That's exact. That's yes.
It works.
Hell yeah.
Is it up?
That should be fine. There's only so many buttons. I think these are on this side. This one.
So you're allocated.
This
So it makes visualizing lifetimes.
Laptop. That might.
It makes it.
Oh.
That's good. That's good. Keep.
Okay, cool.
Flawless.
And then can you figure out what's up on it?
Yeah, I need to.
Yeah, that's.
And then can you
This.
and then send it to me again, please?
This.
It's a really nice. It's a really pretty language. I haven't been in a lot of.
All right, we should be good.
I'll set up whatever this is. Yep. All right. All right. We do have sound. Yeah. I'm not gonna go that. We don't need the whole room. Can people hear me?
Yeah.
Great. Okay. We good on this end? Hold on, I need to do the hand strap.
Need to stay safe. We'll break the projectors.
All right. Hello, I'm Max Downey Twist, and this is my presentation, Trivializing the Impossible, Package Management with a Small Team. For those of you with bad short-term memory, that's my name again. My GitHub, my website, Chrome, which we'll be talking about today, RuroCop Crystal, which is going to be big, and then GCJ, which was big, and then I had to go to year 11. So those are some of my projects. So Chrome Brew, which I'll get into more deal about what exactly this means later, but for now, it'll suffice to say that it's a package manager for Chrome OS. My personal involvement with Chrome Brew dates back to March 2022, when I added the package because I wanted to install it on what was at the time my school Chromebook. I like the team, I like the code base, and I've been working on it ever since. Speaking of, here's the team. That's me again. I'm an Australian university student, for those of you who didn't gather. That is Satdaru Pramanik, Sat Mandu, he's a doctor in New York. Ed Veal, Uber hacker, programmer in Texas. Subi Chicken, he's a Hong Kong high schooler. We don't know his real name. So, introduction. We're going to go over what is package management, what is a package, a brief technical overview of package formats, management backends, and then the languages you write them in, and then just solving problems, package file formats, adding a package, updating a package, fixing a package. Okay, what is package management? It's managing packages. Thank you all for coming. No, package management is installing packages. This often involves building the package, and then ideally you do want the package to work. It's a big thing there. Everything else in package management stems from this. So dependency management, configuration options, security patches, bug fixes, it all comes down to installing a functional package. So everyone is a package manager. Linux, APT, RPM, APK, Nix, Pacman, MOS, Portage, ERPKG. Mac OS has Brew or Homebrew or Mac ports. Even Windows has some. It is Chocolatey, it is Winget, it is Scoop. Some languages even have one too. So Ruby has Gem, Rust has Cargo, JavaScript is NPM or Yarn or PNPM or Bun or Berry, which is just Yarn again. Python, you got so many with Python. You got Pip, UV, Poetry, Hatch, PDM, Conda, Minikana, Mamba, Pixie. There's more. I couldn't fit them all on there. But Python, many package managers. Everything is a package. Top right, packages for Grub, 525. That's your bootloader. Your bootloader is a package. A Linux distribution is just a collection of packages. You can change an Ubuntu installation to a Debian installation by changing the sources and then just APD upgrade. I know I do this in my CI for some reasons. Derivative distributions are just package modifications. You hear Fedora-based, Arch-based, Debian-based. That's because they take Debian packages, Debian's package manager, and then add their own packages. Now, not all operating systems are like this in the sense that they are just all packages. So Chrome OS and Mac OS, they have bits of the system that are not installed by a package manager. And then you do have certain toy operating systems like Linux from scratch or Windows that really aren't designed for package managers at all. They're not very practical. No one uses them. What is a package? So earlier, I said that everything is a package. That's not really helpful. From a user's perspective, what a package is more of a philosophical question. But for a package manager, a package is a collection of information. Most important is the information required to install a package, which we went over earlier. It's part of package management, but this does get surprisingly complex. And then you do want metadata. So, your version, your homepage, your license, your name. It's actually a big one. Most package managers do include the name as part of the metadata. So, a technical overview. Remember that a package manager is not just a collection of package files, but it's also the tools required to build and install the packages. You can subdivide this further. You can split them into a front end or a back end, APT and DPKG. You can have multiple sources of package files, Ubuntu PPAs, Brew casks, and then you can have precompiled binaries, which is basically everything but Gentoo, although they do precompiled binaries now. And there's more, but for today, we're just going to focus on the tools and the package files, a brief outline of the problems they face, and comparing different approaches to solving them. Package files. Earlier, I said the packages were collections of information. This information can effectively be divided up into two types, both of which present their own unique challenges. Static information, name, version, license, homepage, dependencies. Instructional information, build instructions, install script, configuration options, remove script. This creates a problem. So data formats well suited to holding instructional information or static information like JSON or XML or YAML TOML, they're not well suited for holding instructional information. You don't often hear about a install.json file for good reason. And likewise, options suited to holding and executing instructional information, like a shell script, they're not that well suited for holding static information. You don't really have any bash-based databases. And then management backend. So a package manager backend needs to be able to post both of these kinds of information and then execute the instructional and variety in order to build or install packages. And beyond that, It doesn't need to be able to, query and interact seamlessly with the system, manage complex file and network operations, and then you want it to be as robust and self-contained as possible. If your package manager has a lot of dependencies, you can't install the dependencies at the package manager, and the bootstrapping, it's no good. So a package manager needs to be able to store metadata, store instructions, parse and act upon metadata, and then parse and execute instructions. So as a result, most package managers will use different languages for different tasks. And this has the benefit of enabling deep specialization. Or some package managers create their own custom language, like NixOS, which in a sense trivializes this because your language can be whatever you want it to be. So here are some distributions. The backend, metadata, instructions. Just a quick overview. Gentoo, the backend is Python. Metadata instructions are in the custom ebuild file format. Arch, backend is C. Metadata and instructions are in Bash. FreeBSD, backend is C. Metadata instructions are in Makefiles. NixOS, backend is C++. Metadata and instructions are in Nix. Fedora, backend is C++. Metadata instructions, custom RPM spec. Debian, the backend is in C++. The metadata is in the custom control file and some other things. And the instructions are in Make. The VCPKG, the metadata, the backend is in C++. Metadata is in JSON, and the instructions are in CMake. Yay, CMake. Chocolatey, the backend is C#. The metadata is XML, and the instructions are in PowerShell. Some of you may remember that Chocolatey is Windows-based. Could you tell? Distribution, Glaucus. The backend is in NIM, which isn't real. The metadata is in TOML, and the instructions are in POSIX-compatible shell. But this isn't good enough. None of these are good enough. They all suck. Different files for metadata and instructions increases complexity, particularly when the two interact. If you've got like a version-dependent path, your JSON, your CMake have to talk to each other. No good. And then writing a custom language comes with a huge maintenance burden, so that's out of the question for a small team. There's 4 of us. We can't maintain our own language. And then note that languages are a lot like partners. Initially, it might seem like a great idea to have 2 or 3 or 4 of them, but it does actually get pretty complex with their interaction. So ideally, your backend and your packages are in a unified existing, so one that you didn't make up, like NIM or Nix language. But such a language needs to be able to do quite a few things. You want to be able to execute from text. You don't want to have to ship compiled binaries to update your package files to then update your packages. Self-contained commutable dependencies, we went over this earlier. And then you do actually want sustained or total backwards compatibility. Again, for the dependency bootstrapping issue, if you have to rewrite your package manager every 3 weeks, we wrote it in Lua, no good. This is not a comprehensive list, but you get the idea. However, these requirements are absolutely satisfiable. In fact, there is one language that does all this and more that is unequivocally the best tool for the job. CoffeeScript. So, CoffeeScript is, wrong slide. Ruby, here we go. Ruby is a high-level, interpreted, object-oriented, garbage-collected language with a dynamic typing or optional static typing, a powerful standard library, simple expressive syntax, and it's reflective in a good way, not Java, in a good way. There is more. It is optimized for programmer happiness. It's actually faster than inline assembly. It's able to trivially recover lost float precision. It's used at NASA for mission-critical software. I hear that the Moonlander actually runs on Ruby. It inspired all of the good bits of Rust. If you go to the Rust documentation, when it says inspired by, under all the good bits, it actually says Ruby. And so much more. We don't have time to get into all of this, but for now, Ruby is the best language of all time, and the bits that are important is the high-level, object-oriented, good syntax, good library, and good reflection. What does all this look like? So I've talked a lot about languages in theory and practice, splitting up. To explore the pros and cons of various approaches, let's take a look at the same package, FreeBSD, don't know how to pronounce that, across multiple distributions. It will be Debian, Fedora, Arch, and then Chrome Brew. Some things to keep in mind about it as we go on. It is a dual auto-tool/Mason build system. It has no dependencies. It has built-in unit tests, and it's hosted on GitHub. It has release tarballs and Git tag releases. Let's start with Debian. This is Debian's control file. Well, no, it's a third of Debian's control file. I couldn't fit it all on screen. The important bits here, there's the home page. That's about it. Oh, the architecture. And then you can see it's split up into multiple packages. The description, another description, 2 links to the same thing, dependencies, We said earlier it doesn't have any dependencies, so good job, Debian, for finding some. Maintainer, uploaders, the name again, priority, section. This does go on, as I said, for 3 more slides, but I didn't put it in there because we got places to be. More Debian, the license file. Just the entire license file, licensed 1, 2, 3 times. The name again, the license name again, more copyright, and then a copy of the license, including a link to another copy of the license. The only relevant bit here is LGPL 2.1 plus, but whatever. Debian license separate file. We continue on. This is the changelog. It's not the full changelog. Again, the changelog goes for about 1,000 lines. The only reason I put this in here is because the only place the version is stored for a Debian package file is in the changelog. That right there is the way you get the version. You post the latest bit of the changelog. So if this isn't in here, you don't know about the version of your package. Continuing on. This is the actual build bit. This is the instructional information here. You notice it's a make file, but it's not really a normal make file. We said this is a AutoTools or Mason build system. You don't see AutoTools here. All you see is DH auto configure. That is a Debian wrapper for a bunch of different build systems. And the only relevant bits here, it configures it, and it passes enable malloc and enable static. Both of these flags are on by default, but that's cool. Pop off Debian. Then the unit tests. I did say FreeBSD has its own unit tests. Debian does not care. Doesn't even run FreeBSD's unit test. You can see here, no make test or no Mason test or anything. It has its own test. All this test does is, I mean, you can see it. They put the headers in the package config file in the right place. Great test, Debian. Fedora. This is the RPM spec file. And you can see it's already quite a bit more compact than Debian. You have a summary, a name, a version, a fake version, a URL, the source, the license. License is 1 line. Huge improvements. More dependencies. Again, this program has no dependencies. Good job, Fedora. And you can see it's determining what build system to use based on the version of Red Hat Enterprise Linux it's using. Then you've got the description, and then another description, and then another name, because they split up in 2 packages. And you've got the very beginning of the build here, auto reconf -I, or auto setup. It continues. It deletes some files from the archive. Great, good for it. And then you got the build. It's got like 5 different versions. So you've got the RHEL version, the RHEL 5 version, RHEL on PowerPC, other PowerPC. The only bits that are relevant here are, again, Mason, Mason build, or configure and make. All of this could be like 2 lines if RPM spec was good, but it's not. And then you have the make test, you've got the test here. Fedora uses FreeBSD's built-in test because it's not stupid like Debian. We continue. The install. Pretty simple. Make, Dester install, or Mason install. Then does LD config stuff. This sucks for everyone. Removes the LD config, does its own LD config. And then you can see it splits it up into its own files here. Again, regular and then devil. Ooh, mood lighting. And then you got a bit of a changelog. Again, this is not the full changelog because the file here goes for 392 lines.
I'm sorry, this was a bad start. I was like, can we turn off the floodlights to make the slides more visible because projectors are terrible at dark.
I liked it in the dark. Anyways.
It ruined the video quality though.
Oh, it was alright.
Arch. This is the package build file, bash script. Again, we're getting down to business here. Name, version, fake version, description, URL, architecture, license. That's the wrong license, but that's fine. Dependencies, more dependencies, the name of the library, the commit hash of that commit, and then an empty line that shouldn't be there if PKG builds were better. This doesn't need to be here. Again, the relevant bits here, Mason configure, Mason test, Mason install, Vim configuration options. Yay. That should definitely be there and not in your editor config. This is already more compact than Fedora and way more compact than Debian because it only supports one option. It does Mason and doesn't do any PowerPC nonsense. It does have an entire 3 lines for changing directories, but anyways, this is just one file, so it's pretty good. And finally, we get to Chrome Brew. The first thing you will notice, this is 12-point font. 9-point font, 12-point font. It's a smaller package file, And we get down to business again. Description, homepage, version, only one version, and it's the right version. License, compatibility, source URL, the Git hashtag, and then this is only here, that's the binary download hashes. Those are only there because we bundle everything into one file. If you want to do a fair comparison, you would delete these because these are stored server side for everything else, but we seem to be doing fine without a fair comparison. Then we have our Mason options here. We disable documentation, and then we run tests. Just one line, run tests. You will also notice, where is the Mason build? Where is the Mason configure? Where is the Mason install? Up there. Ruby object-oriented. This is a Mason subclass of the package class, and that wraps all the boilerplate for us. So we're down to like 20 lines here. So all the distributions, they're packaging the same package, same file, but there are a number of key differences. Debian splits it up into several different packages, then splits those packages into several different files. It carries its own copy of license and uses its own test files. Fedora, Arch, and Chromeboot, same general idea. Fedora supports both build systems and does more conditional configuration, and it's much larger as a result. It's, again, 3 slides. Arch and Chromeboot were basically the same. You see, basically the same, but Chromeboot skips the Mason boilerplate with the Mason subclass, and it's much smaller as a result. Also, you can notice that there's no equal signs there. That's for some package-specific metaprogramming. Most Ruby has equal signs. So some of the differences are technical. Chromeboot can create a Mason subclass of the package class because Chromeboot package files are just Ruby files, and Ruby has great ROP. Arch can't do this because their files are bash files. Bash does not have OOP, as far as I know. In this case, both Arch and Chromeboot, we're trying to do the same thing. We're just better. But some of them are philosophical. So we don't have a changelog in the package file like Fedora and Debian because we're hosted on Git, and a changelog is just a duplication of Git history. We don't have local tests because upstream has tests. Tests are good enough. We don't have a license file because we have the name of the license, and it's the same license corresponding to the name everywhere. This works. This is a good jumping off point to a bit of an organizational overview. Just an explanation of why we make these decisions. As described earlier, Chromeboot is run by a small team. On a good day, we average 3 maintainers total, just because some of us have lives and are asleep. But we maintain 2,482 packages, meaning each one of us, like me, is responsible for about 827 packages. That's not to mention dealing with the infrastructure, the backend, or users. 827 packages is a lot. For comparison, Debian developers, seen here, handle a little over 4 packages each. So as we continue, just keep that in mind. Keep in mind that disparity and the role it plays in the decisions we make when it comes to how we solve problems. We are managing a lot more packages than they are. Oh, a minor disclaimer. We actually only maintain 2,481 packages. Jason Pratt, seen here, has taken it upon himself to maintain the Terraform package since 2022. On the right, here's some of the 40 pull requests he's done as part of that. He's always there. Just 41 every single time. Great guy. Let's take a look at 3 major problems package managers face and compare the different approaches taken by Debian and Chromeboot and illustrate these with specific examples. So we're going to talk about adding a package. We're going to use libversion as an example. We're going to talk about updating a package, Mesa as an example, and then fixing or patching a bug in a package. We will use libedit as an example. Adding a package. I didn't want to know what time it was anyway. That's fine. In Chromeboot, you make a pull request. In Debian, first, follow steps 15.4.1 to 15.4.2.5 of the Debian Administrator's Handbook. Join an internal Debian team. Create an account on mentors.debian.net. Read the 89-page Debian packaging tutorial, in addition to the handbook. Upload the package on mentors.debian.net. Ask the Debian Mentors mailing list for a sponsor. File a RFS bug against the sponsorship request's pseudo package. It keeps going. I just didn't have time to put it all on here. So let's take a look at the process of adding a package to Chromeboot. Libversion is an example. First, you make the package. Seen here, description, homepage, version, license, compatibility, source URL, Git hashtag, Then to CMake, so we just put CMake, run tests, done. Again, this bit handled automatically. This took me about 10 minutes to do, and most of that was just finding the home page, the license delayed version, and then checking, oh yeah, this is CMake, and then put it all in the package file. I then used the build package workflow on our CI. Took 15 seconds to fill out our branch name, which was lib version, and then I waited 10 minutes for it to be built, and the change to be pushed, and the PR was made automatically. PR, seen here. That was made automatically, and approved, reviewed, and merged. It took a little under 2 hours for this to get reviewed and merged, and that's longer than usual because it had a special case. For comparison, the first Chrome boot package I ever made, libbitesize, took me about an hour to make, and then took a few days to get reviewed and merged. I was about 15 at the time, and I have clearly gotten faster and better as I've gotten older, but even for a literal child, contributing to Chrome boot was pretty easy. Again, 15. I was like in the middle of history class. This slide was supposed to contain images of me adding lib version to Debian. You may notice no images. The barrier to entry to doing this was high enough, the 89-page tutorial, that it was easier to build this package from source every single time we run our CI than it was to add to Debian. As I said earlier, Chrome boot, simple enough to contribute to that a child could be a maintainer. And in fact, many are. The project was started by a child, and there have always been children on the core team. Right now there's only one because I got old and washed up, but it's like, meanwhile, as an adult with several years of programming and package management experience, I couldn't even figure out where to start after trying for 3 days. I didn't get to the, I read the 89-page handbook, I filed the mailing list bug, whatever. Again, am I personally stupid? Yes, of course. But does that excuse Debian's barrier to entry? Like, probably not. Updating the package. In Chrome boot, you update the package version in the file, you run the build workflow, and then you or someone merges the generated pull request. Now, note that the first and second steps are automatically done. We have CI that automatically does this for most packages, so you only have to merge a pull request. But in worst case scenario, you have to edit the package version in the file, click run build, and then merge. Debian, not that bad. Update the package version in the changelog. Rebase a patch quilt. Locally build the new version of the package. Find the binary, submit the build package to the upload queue, and then accept the upload in the relevant branch. Let's take a look at what this looks like for Chrome boot for Mesa. Step 1, update the package version. Seen here. A little small, but you get the idea. A one-line change, you change 2 numbers. Step 2, run the build workflow. Build workflow, seen here. You type in update Mesa or whatever you name your branch on, and then all this is set up by default, and you click run workflow. The pull request is automatically generated. Pull request, seen here. That's a pull request. This was 3 days ago by now, but get the point. And you review and approve the pull request. Approval, seen here. We have auto merge set up. So you just approve it, and then you're good. Debian. Step 1, update the package version in the changelog. So, update the package version. Again, it's not that bad. This isn't actually the right update because there were like 3 different updates for this that I couldn't find the right one for, but pretty similar. You change a few lines. You build the new package version. This is an excerpt from one of the 3 Debian manuals on how to build a package, but it's just one command, usually. dpkga build package us uc, and then you install the right dependencies. Other architecture will be built automatically. So if you are on x86-64, the ARM or the PowerPC or the Spark versions will all be built automatically when you upload it to the build queue. But you still got to do your local version yourself. We continue. Step 3, you sign the build package. Just, deb sign, then use the deb sign command. Not that bad. I mean, you do need the GPG key, but whatever. You upload the build package. Again, excerpts, you make your own dupload config file or dput, but let's go with dupload for now. You read the manual to make your config file, you set the default host, and then you upload the file. Not that bad. Keeps going. You just review and keep the upload in the relevant build branch. That's what this looks like here. Mailing list, obviously, changelog, checksums, distribution, urgency, source, format, maintainer, Debian, X, Strikeforce. Fixing or packaging a bug in a package. In Chrome boot, you open a pull request, you fix the issue upstream. Then this part is critical. You sit and you wait for the pull request to be merged. And you update the package. This doesn't work if upstream is inactive. And an inactive upstream is a massive pain for everyone. But stay tuned for Project Waterfall to alleviate this. I'm going to get some water to alleviate my thirst. Where did I put my water bottle? Aha. That should come across great in the audio. Sorry about that. Continuing on. Debian. You patch the issue locally. You add the patch to the patch quilt. You fill out the attached patch template according to the patch tagging guidelines, version 3, 2024. You rebuild the package with the patch, and then you rebase the patch with each update. Now, it does say, and again, one of the 2 separate Debian patching guidelines I could find, that if possible, you do submit the patch upstream. Let's see how that actually turns out. Chromeboot. Step 1. Open a pull request to fix the issue upstream. This is actually not a pull request. This is an email. I needed an email instead. This is for, again, libedit. They didn't, or edit line. They didn't have a GitHub. And so email. Wait for the issue to be fixed upstream. Waiting, seen here. Fixed upstream, seen here. I just say there's an issue. They fix it. Step 3, update the package. We did go over this earlier. Again, trivial, you know. I think libedit was actually automatically updated after I did this, so that's kind of cool. Debian. Step 1, add the patch to the patch quilt. Just, you know, change log, the patch. The actual patch here is a little under 2,000 lines, so I couldn't fit that on the slides. But, you know, just quick, easy thing, 2,000 lines. You rebase the patch with each update. Definitely happening here. 2018, rebase the patch. 2021, rebase. This continues down to about 2004, which I couldn't fit on the slides here. But, again, 2,000 line patch, rebased for about 20 years. Good for you, Debian. Step 3, you submit the patch upstream, right? This is the Debian libedit package. Note that it is saying you should submit these 6 patches upstream. So that's cool, right? Last update 2025, but don't worry, they submit the patches upstream. Right? See here, patches, not submitted upstream. Famously, not upstream. Big no, right there. A quick note. This bug in libedit was introduced in 2004. 2004. They had 20 years to submit upstream. But it's not just Debian. 65 different distributions package libedit. Out of the 30 I checked, 10 have patches or workarounds for this bug. Assuming that ratio roughly holds, this bug has existed for around 400 collective years. In all that time, none of them fought to upstream the fix. But when I say Chromeboot, we don't have the luxury of inefficiency, I'm talking about this. 2,000 line patch, 400 years. I wrote an email, took 10 minutes. Again, middle of history class, email, 10 minutes. It's not that hard. In conclusion, I'm going too fast. Anyways, in conclusion, patch management is a lot of work. Chromeboot is successful despite a small team because we minimize the work. It includes a simple package format, which we covered earlier, Debian, 8 slides, Chromeboot, 1 slide, a simpler development process, 1 pull request, no 89-page manual, and a strong focus on upstream collaboration. For example, when a bug has existed for 20 years, we fix the bug. We fix the bug. We don't stand around going, we should upstream this, right? We should upstream this. We should probably upstream this. It's been 20 years. Should we upstream this? No, we shouldn't. Apparently not. Strong upstream collaboration. Bonus slides. This is just a random collection of slides I had lying around that didn't fit nicely into the narrative. And I'll see how many I can get through as time allows. I can't count. How much time do I have? Plenty. Dependency question. The dependency question. One of the main problems in package management is dependencies. You know, you've got your version, your ABI breaks, backwards, forwards compatibility, etc. Linus Torvalds said, that's what I fundamentally really think needs to change for Linux to work on the desktop. He talked about how Valve was going to solve it. Spoiler alert, Valve didn't solve it. Common Valve L. This problem does manifest itself differently depending on your language, your ecosystem, the availability of source, and each solution is a trade-off between compatibility and efficiency. Let's take a look now at some of those solutions arranged nicely in a table. Table, seen here. So, first up, we have doing the work. This is what a normal package manager does. You just install the dependencies system-wide, and if they break, you fix them. You got ABI compatibility. Is it easy? No. Is it efficient? Yes. Is it compatible? Does it work? I mean, most of the time. Is it scalable? Yes. Who does this? Debian, Chromebook, Fedora, Homebrew, Alpine, more people. Static linking. This is when you just embed like most of the library you're using into each copy of the package file. Is this easy? Yes. You're not doing, get back there. Is it easy? Yes. You're doing basically little work. Is it efficient? Not really, because you're copying every single library into each package and duplicate across the entire system. Is it compatible? Yes, because you're not doing any work. Is it scalable? Again, not really, because it's not that efficient. Who does this? Rust does this. Go Rust. What distributions do this? None. Oasis, Stolly, they don't exist, and they're not real, and they're really small. Basically, no one does static linking on a large scale. But library vendoring. Is this easy? Yes. Is it efficient? No. This is when you copy every single dynamic library your package uses into a folder and call that sandboxing. Is it compatible? Yes, because you copy every single library. Okay, here's the thing. Static linking, right? You take only the bits of the library you need. So let's say you use FFmpeg only to convert images. When you statically link, you only take the image code. When you library vendor, you take the entirety of FFmpeg every single time. So if I have a VLC regular package that has FFmpeg, and I have a statically linked one, the statically linked one will be a little bigger. If I have a library vendored one, that will use the entire concept of FFmpeg. Is it compatible? Yes. Is it scalable? No, it is not scalable. Why do you think there are no distributions based entirely around Snap or AppImage or Flatpak? Despite Fedora's best attempts, you can't do everything in Flatpak. Also, if you scale Flatpak up to a full system that is a regular package manager again, but except you just copy every dependency like 40 times. Steam does this as well. In the talk earlier, this one, good talk, watch it if you want. Linus Torvalds said, I think Valve will solve this because they're going to statically link everything. However, he is kind of stupid from time to time, and you can't statically link if you don't have the source code. You don't have the source code to compile proprietary games. So Steam does library vendoring. Steam Runtime is a copy of Debian. Your Steam bundles about 6 copies of Debian with it. Did you know? Fun fact. Now, we've got a very, very good option coming up. Not doing the work. Is this easy? Yes. Is it efficient? No. Is it compatible? No. Is it scalable? No. Who does it? JavaScript and Python. Does JavaScript actually vendor dependencies? Sometimes. Does Python? No. Again, not doing the work is very tempting because you don't have to think about it. Python dependency hell, as you talked about earlier, is mostly exclusive to JavaScript and Python. You don't talk about dependency hell.
And that occasionally.
Occasionally. But again, is it compatible? Sometimes. Is this compatible? No. Never. Because when you install a Python package, as you know, it doesn't work, as I know, because Python doesn't do the work. However, we've got one very nice option here. Being better. That should be a check. Oops. Being better. Is it easy? Yes. Is it efficient? Yes. Is it compatible? Yes. Is it scalable? Yes. Who does it? Ruby and probably Crystal. When you install a Ruby package or you use a Ruby bundle, every dependency is installed system-wide. And the bundle just takes those copies system-wide. Imagine if you had a virtual environment without the virtual environment and your packages just worked because your language is better. Wouldn't that be neat? Anyways, oh, a reminder, everyone in the team is volunteering in their spare time. I'm a full-time uni student, and I have 2 full-time jobs, or 2 part-time jobs. And then Ed Veal, Uber hacker, he's a professional programmer by trade. Sadaru, he's a doctor with more doctor things there. I think that's mastery in public health. But everyone still works incredibly hard. You can see here, that's working incredibly hard. Almost all of these are package updates or pull request reviews. Like, I don't get how they fit in the time. Is Sadaru like scalpel, pull request, scissors? I don't get it. He's got 2 kids. How did he fit in the time? I don't know. But we all work incredibly hard. Again, Debian developers maintain 4 packages. We maintain 827. Are we working 200 times harder than them? No, because we minimize the work. Are we working 50 times harder than them? I mean, yeah, probably. This is evident by the fact that Chromebook has Ruby 3.4. Debian doesn't. Anyways, this is a minor thing. Rust not having dynamic linking is really bad. Really bad. Seen here. That's bad for binary sizes because, as I covered earlier, every Rust program includes every copy of every dependency it uses. So here's an example. Fish, great shell, used to be written in C++. It was 8.76 megabytes. Now that you write it in Rust, it is 21.4 megabytes. That is not good. That's more than a doubling in size. You can't do that to all of your packages. So before you rewrite it in Rust, why don't you fix Rust? It's bad for compilation times because every Rust program builds its own copy of every dependency it uses. For those of you who use npm, you know when you type npm install and it installs 700 packages, 84 looking for funding, 3 maintainers need a hug, added 14 security vulnerabilities. That's really bad. But because JavaScript is interpreted, you don't pay the price for that. When Cargo does that, you build all 700 of those packages from source every single time. I know. Chromebook does it. It sucks. Debian does it. It sucks. Debian has complained about how bad it is to build Rust packages because you don't get any of the benefits of dynamic linking, which we figured out is a good thing to do in like the 1950s. Catch up, Rust. Anyways, don't use makefiles. Talking to you. You specifically. And anyone else thinking of using makefiles, don't do that.
Can you tell us DCC as well?
Don't do that. Makefiles lack standardization, which means every package, like yours and yours, that uses a makefile requires bespoke arguments and configuration. There's a reason, Chromebook, we have package subclasses for Mason, AutoTools, CMake, QMake, and the rest, but nothing for makefiles. Nobody does. Debian doesn't, Chromebook doesn't, because the lack of standardization makes this impossible. So the average CMake package doesn't include any additional work from Chromebook. You saw that with libversion. The average makefile package, no matter what, does, because we don't know how you treat dester or prefix. Do you swap around dester and prefix? Plenty of people do this. Don't do that. If you use a makefile, come see me after the presentation. This is another thing. You don't need to build on Docker. Seen here, Creda, which thinks it needs to build on Docker. Unsupported regular building. Your package is not so complicated that the only way to build it is in Docker. It's just not. By assuming that it is, you make it harder for the distributions actually packaging it, doing the work to do it properly. Building packages is hard enough without upstream going, actually, our software is uniquely complex, and so we're going to give up on building it normally. Seen here, giving up. It's not that deep. You don't need Docker. We package Creda without Docker. They can manage, but it's harder because Creda assumes you have Docker. Blender is even worse. Similarly, don't vendor your dependencies. You don't need to do it. Seen here, this is shader.c from Google. An open issue to sanitize the build system for packages. 6 people say, yep, you should do that. Another guy says, yes, this is a nightmare. Spider web dependencies in poor design. Seen here, maintainer. The cause of the complexity is that shader.c is built in various configurations. Also, the current setup just works. Shush. No. Everyone else has managed this for the past 20 years. I cannot emphasize enough that your problem is not unique and it can be solved normally. Everyone else manages to use their dependencies normally, not clone them in and build them manually every single time. Because now Chromebook has to ship 3 copies of Vulkan tools because shader.c can't get... I don't like this. Don't do this. Don't vendor your depths, man. Don't vendor your depths. Be a good OSS citizen. Don't use a makefile. Don't hardcode your installation prefix. It's probably one of you. Don't do that. Don't use a non-standard build process. Don't be Creda. Don't be Blender. Don't vendor your own dependencies. Really, don't vendor your own dependencies. Especially if you don't even support using the system ones, like shader.c. Like, Dolphin uses its own dependencies by default, but it supports system versions. That's good enough. We can package it normally. Don't use scons. Just don't use it. It's not very good. Pretty bad. Doesn't let you customize installation directories. Don't use it. None of you have heard of SCons, but that's fine. Some slides that were cut for time. The image over there in the top right, that is the logos of Snap, AppImage, and Flatpak. Too many cooks in the kitchen, spoiling RPM. Other things that were cut for time, more complicated packages, more complicated package management backend, a detailed explanation of static linking with dynamic lib bundling, a live demo of me updating a Chromebrew package. The package I was planning to demo got automatically updated last night while I wasn't looking. We're too good. And then why NixOS's maintenance burden grows exponentially and why it's actually not good. Is that all? That is all. Do we have time for Q&A or perhaps a live demo? Yikes. Live demo, Q&A. You've got the mic. Oh, clap. Clap.
Question.
In 2521, don't you use make files?
Yes. If you see all the way back here, notably, 2F2 is nowhere to be seen in the solving problems section. That's unrelated, but I just want to point that out. In 2F21, we use makefiles, but you never ship anything making 2F21 to the outside world because it's, it's useless. It's solving problems. It's for children and toys. But yes, they should be using anything else in 2521. Well, they shouldn't be doing 2521 full stop. Down with 2521. Does that answer your question?
Yeah.
CMake.
Yes, but that's okay, not good.
Mason.
I haven't looked very much into it, but
It gets the job done.
okay.
In my 827 packages of experience.
Can you quickly go back to the very last slide again, the slides cut for time?
Yes.
Yeah, why is NixOS's maintenance burden growing exponentially, and why is that actually not good?
So,
You told me this earlier, but I think it'd be interesting for others.
So as you said earlier, and as I've experienced, NixOS keeps every single version of a package. So yes, you can install Gradle 8.8. That's great. But what that means is you have to keep every Gradle from 1 to whatever they use now, and you have to keep that functional. So whenever NixOS adds a new version of the package, that just stays there. It stays there. They do not remove the old version. So Chromebrew, we ship one version of Gradle. NixOS ships 30.
Arguably, the reason I can get the old version of Gradle is because I was literally going back through their Git history, which is
Yes.
cursed.
Not only does their maintenance burden grow exponentially, they don't even distribute it efficiently. You couldn't find that effectively, despite the fact that they did the work to do it. Anyone else, or did that answer your question?
That answers the question.
Is Chromebrew faster than inline assembly?
Consult the slide. Yes, it does. Seen here, Ruby is faster than inline assembly.
Yeah, you run it with C Ruby though.
Speak for yourself. We may not ship truffle Ruby, but we could. We could.
Sorry, yeah, can you go back to the slide with the trade-offs for the different ways of doing package management?
Yep. Which one?
The one where you compare doing the work, not doing the work.
Yeah. Dependency management.
Yep. Yeah. I was wondering, you maybe did mention it, but I might have misunderstood or missed it. Could you go a bit more in depth on how Ruby and Crystal do this and what you mean by being better?
I'd be happy to. So when you install a Ruby package, or not, you use gem install system-wide. That works flawlessly. When you're developing something, you use a bundle file, which is a little bit like a requirements.txt or package.json, but it's better because it's written in Ruby. But the key thing here is when you run something, you do bundle install or bundle exec. This installs them system-wide. So there's no node modules. There's no virtual environments. Every package you need is installed system-wide, and that is shared and that is reused. So Ruby doesn't have dependency hell because you can always install the right version of the dependency, and it will always be reused. So it's space efficient, it's easy, it's compatible, it's scalable. And then if you're developing a package, you get bored of the package, you delete it, you do Ruby gem cleanup, and that deletes all the gems that don't have a bundle thing linked to them. Last I checked, pip did not have auto remove. So yikes. But yeah, so basically, it's just better because A, it's Ruby. Please see the blog and the slide. But also because dependencies are global, they are system-wide, they are shared, and they are always compatible. You can install as many as you want next to each other, and they're cleaned up after you're done, if that's what you so choose. So when I work on different versions of Rubocop when I forget to fetch my home directory. So as a result, I have like 6 different versions of Rubocop for development, but they all work. And when I don't need them, I run gem cleanup, and I go down to the 2 I actually need. Yeah, and then I think Crystal does that. I don't know. I haven't checked. They probably do. Crystal does have the thing where it's compiled, which changes things a little bit, but it's not like Rust or anything. All right. Any further questions? It would seem so.
Yeah, one question I do have is in terms of like you've put Python in the not doing the work category, and modern tools like UV in the Python ecosystem, they actually do the whole like deduplicating packages by using a global cache. So although yes, I know there are many options, and most of them are bad as well. Yes, I'm aware, but yeah, the whole deduplication of dependencies thing is something that Python is beginning to do now. So is it specifically that the problem is that those dependencies are not globally installed? And
so the problem is virtual environments. It's a lack of, as you well know, is a lack of actual dependency pinning or hash pinning in requirements.txt. Again, we've been over this. There are a couple of Python options. I'm sure you're all familiar with the XKCD, where there become 15 competing standards. Python, if UV takes over the world and the next time there's presentation, it's just UV, like Ruby or Rust, that's great. But as of right now, as you said, Python is beginning to get good, but it's not. And the first, if you give a data scientist Python, they will use pip to install their package, and they will make their requirements.txt with no dependency pinning and no version pinning. And when you try and run it, your system will blow up. In Ruby, that won't happen. So, yes, the best of Python is nearly as good as Ruby, but it's not you're not using the best of Python. You're using the regular of Python.
So you're essentially saying that my problem is that I'm too good at Python.
I'm saying the problem is that the average Python user is not good enough. If you are better than the average Python user, great. If you can make every other Python user better, even better. But as of now, you deal with the worst, because again, we handle 2,482 or 81 packages. So I've seen every possible worst case scenario. But in Ruby, the worst case scenario is still pretty good. All right.
Thank you very much.
We'll have Jethro, and we'll just take a bit of time to set up. That's okay. On the average data scientist, one of my group project members literally did that, having to edit conversion of Cairo on the way here. So it's a topical example.
Oh yeah, you need the slides for good, right?
Yep.
Yeah, thanks for coming.
Thanks for coming. Bye.
Thank you. Time delays.
Do you do it for this one?
The QR code is welcome.
Okay, awesome, thank you. That's the only thing I asked of you. Are you also assisting again?
I mean, I could not assist. I could just say good luck.
Why is your work so expensive?
Hang on. I don't think it's good. Wait, I'll let it again. This is stupid.
Normally, this is like a.
It's okay, right?
Yes.
To scan on? To scan off there.
It does, which is freaky. What?
Oh, well, I'll send you to hijack.
I mean, I saw it come up earlier.
Maddie, you still have Bluetooth off, right?
Yes, I do.
Great. I got
Also, I forgot the device.
Okay. Thank you very much.
Well, that's my other favorite known feature. Sometimes my desktop background turns orange and I don't know why.
Yeah, Nintendo RVL TV.
That also happens on Fedora, so it's not his fault.
Then the other.
There.
Um,
Connect. I know your system.
Attempting to connect. I've not used a Bluetooth device on my laptop in like a year.
The answer is that you don't get that.
It's doable. It's doable.
Yes, but Rust developed
and then
a
obviously
very
It's probably going to from the rocks that are actually stabilized. And that
Yeah, maybe.
Maybe it should. Maybe not hold it.
Well, I don't really know how they do it. If they don't follow the way Swift does.
Yeah.
So Swift uses something called the
So I went off. Connect there. Connected
Yeah,
there.
yeah,
Yes, great.
For example,
And then input
the
vmapper.
question is, how would you?
Is it meant to keep flashing?
No, but that's fine. That should be fine.
Okay. Freaky.
How do you use?
Okay, inquiry map up.
Rust does do fun because it like C++ that just calls.
Okay.
So how Swift does it?
Yeah, that should, it should be showing up.
So generics
there.
are will be like,
Connected.
so.
Yeah, like point to Rust because you don't do Rust.
Well, yeah, they're not quite Rust is different, which is why they probably want.
Right, so it should be
It
here.
should be in like the top left there.
That is
Oh,
not
okay.
practice.
Maybe it didn't connect.
Yeah, maybe it didn't have one.
Hang on. Okay, let me run.
So.
This thing
let's
again,
say I
there.
have- I make a,
Connected.
so I make a.
Yep. Okay.
And then
That's connected. Yes, bad. Yes.
Yep, and then it should, that should stop flashing and then any second now, that should be fine. And
Maybe
then
it's at this.
not connected.
What? Oh yeah.
Function pointed to.
Now? Oh, now it's connected. Yes, but that's all for it.
So the allocate.
Hey.
And then check input vmapper and then it might work.
Pull the function.
Uh,
Or allocate it. Look up the function again. So and it's just details for everything. So it's very dynamic.
it's okay. I might just be hitting the page
Then you
now.
have to change the code.
Yeah, failed to connect. Skull. All right. Page down time.
Yeah, I don't know about that. All right.
Oh, good. Thanks for trying.
Freaky system.
I mean, I just haven't set up Bluetooth. That's probably. Alright.
Do you need to, like, there's a slide I just need for you to have a link.
Yeah. Yeah. Okay. What's the link?
V.
Oh.
And then the first thing, and then it'll like when you go on the site, it'll the thing as like remote screen share or whatever, and then it'll give you a link. Which is, and then I just think that.
Then we check.
Yeah, so we'll connect you up to there, and then also the link is just for us to have better life.
Oh, one more thing.
Well, that's the other joy of Mixer is that sometimes to install a program, you don't like add it to system packages, you instead think .enable equals true.
Yeah. I was gonna like mess with stuff, but I'm
Yeah, it's so good and it's so bad.
I'm gonna have some things, and then it's fine.
Alright. Cool. I will now connect this.
And then the link is just all like screen shared.
Normally, when I get I've not had someone already. So I toned it down.
Yay! Just a photo. And then you want to.
You would check that if I saw something like.
Okay.
Oh, and then there's a link at the top.
Well,
If you
the
mind,
problem is here.
send it.
My opinion.
Not that one. So if you go out and then
I know.
What do I do with that?
send it to me.
Already know they were making so, well, everything makes Rust is a language about you, but the main thing I don't like Rust is the dynamic weighting. It's not,
Alright.
designed for you can take it from on. They get better. Like good
Actually,
Yeah.
Everything from Rust, I look in my case record on NetCat. It's 15
First
cases.
one, come up there.
How does that work?
That's
I'm gonna
all
run
weird.
CI, yeah.
Cool.
I'm gonna run when we have to do 40 like work back to build big shell, right? We have to 20 megabyte packages.
All that being
guys, what's that number on the top left?
Which number?
Hang on, I can work out my elimination. 1, 2, 3, 4, it's 5, right? Yeah, there we go.
Okay, cool.
Alright,
Yeah, but it's solvable.
wait.
It's a solvable.
1 second, guys.
No one can agree on how to solve it.
Rustic, not green, impossible. No.
Beautiful. Alright.
It's generally a
It's a funny troll, though.
It's 3 times faster. Please do. Engine X beats.
Is this mic working? Yes? Cool. All right. Okay. Hi, everyone. My name is Jethro. I'm a second-year computer engineering student here at UNSW. My main passion is in hardware, which is why it's kind of ironic that I'm here to talk to you guys today about some really pretty math stuff that I've come across. Yeah, this past term, I've been doing Comp 3821, extended algorithm design and analysis. And yeah, just found some really pretty stuff in maths that I'm going to be talking about. So, little kind of overview. We're going to start by looking at what graph coloring actually is, as well as a brief introduction to Markov chains. I'm then going to present a technique used in probability theory called coupling. Then how that eventually got generalized by some really smart mathematicians into path coupling, which is what this talk's all about. And then kind of just tying all together, talking about what I got out of it, and yeah, what it means overall. So first off, thank you, Linsock, for organizing this very epic event. Thoroughly enjoy the opportunity. Also, 381 course staff, it was pretty good, of course. And then yeah, my group members, they did cool stuff, and my project supervisor, because a lot of my group members' work is in here. So starting off, for those of you who are not well versed in computer science, graph coloring is a pretty famous problem. Basically, you define a graph, right, which is a set of dots and lines between them. And the question is, is it possible, given a set of like a certain number of colors, to assign a color to each vertex such that each adjacent vertex is a different color, right? So here we can see one graph coloring, right? Because none of the points that are connected by a line share the same color. And here we can see another graph coloring, except that this graph coloring is actually the same graph coloring. They're in isometry because the colors, although the colors are different, you can basically just set the green to blue, the blue to red, and the red to green, and you have the same assortment of colors, right? So it's the same coloring, even if the colors are different, because you can just assign the colors arbitrarily. So in terms of like when you're actually dealing with it, mathematically, it's not useful to like talk about it in terms of, yeah, we're going to use like red, blue, green, yellow, and gray for this one, right? Usually you just assign a number to each one, and then you also have a vector representing the coloring, where the index is the vertex and the color is the number at that vertex. Now, the reason it's quite a famous problem is because it is NP complete. Meaning, it is at least as hard as every problem in NP, and also it is, but that's the NP hard part, but it is also in NP, right? So to talk a bit about what that means, if you consider a problem like sorting a list, that's something in P, meaning you can do it in polynomial time. In other words, fast. K-coloring, very, very not fast. So enter randomness. So if you don't really care about doing it deterministically, i.e., you want it to be fast, but there might be some variance in how long it takes. Well, we can do something like the following. Just pick any coloring. Doesn't have to be a valid one. You then pick a vertex uniformly at random and pick a color uniformly at random. And then you look in the neighborhood of that vertex. You check, is that color, neighborhood meaning like any vertices connected by an edge to that vertex. Is that color in the neighborhood of that vertex? If it is, then skip and try again. If it isn't, then update it. Now, this algorithm has a name. It's called the Metropolis chain, and it is a Markov chain. Now, Markov chain is basically just any kind of system where the next state depends, like what the probability of the next state depends on the current state and nothing else. So this is like just one application of them. Turns out you can use them to solve a huge range of problems, which typically these algorithms are just called like Markov chain Monte Carlo methods, is like the general umbrella term for all of them. Another thing that's worth mentioning is that we've kind of, you may notice, by these rules we've defined, we said you can pick any coloring, it doesn't have to be valid. If it is a valid coloring, this set of rules will never generate an invalid one. So in other words, you can transition from an invalid coloring to a valid coloring, but never the other way around. And this will come into play later. So why do we care about this? The short answer is it's fun. But the real answer is it does actually have some applications. So where before the problem was just finding if a k-coloring exists, now we can do something a little more interesting, which is find every k-coloring of a graph, right? Because as I said earlier, once you enter into a valid coloring, you can only transition to other valid colorings. So you can, in theory, just keep running the chain, and you will eventually, under certain conditions, sample the entire, like every valid coloring of that graph. And an application of this is in the Ising model, which is in physics. Say you've invented a new material, and you want to know about its magnetic properties. Specifically, you want to know at what, below what temperature it is, like above what temperature it ceases to become magnetic. So there's actually a Markov chain that describes this called the Glauber dynamics. And it works by sampling a vertex at random, considering, worth mentioning as well, the colors in this are spin states. Your graph is a 2D lattice. You sample a vertex at random. You look at the energies in that neighborhood. And you depending on the energy in that neighborhood, that gives you your probability of flipping the spin. And what you find is that if the critical temperature, if the temperature parameter you give it is above the critical temperature, then it will converge to the state space of to a state space of a lot of different colorings. In other words, you can just keep running it, and it'll keep sampling from like a massive wide range of configurations. Whereas if you're below the critical temperature, it will converge to a single coloring and basically never move from there. Cool. Now we've got the boring part out of the way. Let's talk maths. So, as I said, under some conditions, a Markov chain can converge to a stationary distribution. In other words, instead of the next state only depending on the current state, you can basically just treat it like a normal probability distribution for all intents and purposes. And this can be represented by, we call this the stationary distribution. We denote with pi. P is the transition matrix of the Markov chain, which we'll look at that a little bit. And some of you may recognize this as basically saying that the stationary distribution is a row eigenvector of the transition matrix. Now, there's a lot of conditions that force this to happen. I won't go into too much of it, but the two kind of main ones is if you have a chain with a self-cycle where every state is reachable from every other state, then your chain is probably ergodic, meaning that the stationary distribution, meaning that it has a stationary distribution, basically. That is reachable. So I think Krita was mentioned earlier. Krita, my goat. Thank you, Krita, for providing great code, and also thank you, Arch Packages. I did not know it was that difficult to to do that. So let's look at an example Markov chain, right? This has got two states. The probabilities of going from state 1 to itself is 0.9, from state 0 to itself is 0.8, and then between them is 0.2 and 0.1. So you can represent that as the transition matrix, right? Where basically the 0, 0 element corresponds to the probability, if you're in state 0, of going back to state 0. And this 0.2 corresponds to your in state 0 and you're going to state 1. And you can find that it does have a left eigenvector that is 1/3, 2/3 with an eigenvalue of 1, right? Which basically means that if you run this chain indefinitely, it will just converge to this distribution, right? Of telling you where this corresponds to the probability of finding an object in state 0 and the probability of finding an object in state 1. However, if we look at another example, in this case, probability of transitioning between them is 1 and to themselves is 0. Well, there are some row eigenvectors, but this one you may notice, no matter how many times you raise this to some power n, it's never going to reach this. It's never going to reach this vector. And the problem with this vector is that it has an eigenvalue of -1, meaning that basically each time you run it, it's going to flip to the other side. And this one is reachable. Obviously not this exact vector, to be a scalar multiple of it. And that corresponds to basically, if we look back here, if you start in a configuration of, say, like, I don't know, 1, 0, right? So like 100% of your objects are in this one, then it's just going to keep oscillating back and forth. And so you're never going to hit a stationary distribution because it's just going to keep, the stationary distribution is going to oscillate with a period of 2 steps, right? Cool. So now we're going to talk a little bit about mixing time. So first of all, the total variation distance is a measurement of basically the difference of 2 different probability distributions. It is basically, if you have 2 distributions, mu and tau, and you want to know the total variation distance between them, you basically just look at like the maximum over the probability space, the maximum difference between them of that event occurring. They have to be defined on the same probability space. That's another important thing. And the definition of the mixing time is basically saying that this notation here basically means the probability of finding between p of x 0 and pi. Yeah, probability of an event given any starting configuration and the stationary distribution. That's what this means here. The dot means basically any starting configuration is less than some epsilon, which is arbitrary. However, it can't be more than 0.5. Otherwise, it is just completely irrelevant, doesn't mean anything. And typically, people just say a quarter is a good measurement for that. All right. Now, got all that out of the way. We can start talking about some of the actual cool methods that have existed in the field for quite a while. So, what is coupling? Well, coupling is a method that basically you condition 2 random variables on each other, such that you can say something about them. And oftentimes this corresponds to, like, you create an inequality between them, which lets you then prove something else. Strictly speaking, it's defined as this thing here, where these are once again distributions, and you're basically defining 2 new variables such that the probability that x is some state is equal to the probability that that distribution is that state, and same thing for this one, right? In other words, you're relating the marginal distribution of this one with respect to x is that, and same here. And we're going to look, this is all very abstract at the moment, but we're going to see how you can apply this to show some really interesting things. So an example is, say you want to do the random walk on a hypercube. So you can represent, say, just like a 3-dimensional cube, right? you can represent the vertices as coordinates, right? So say you have it start at 0, 0, 0, and the opposite corner is at 1, 1, 1. Then you basically have coordinates for like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? And so you can basically just represent a vertex of the hypercube as a binary string. And so we're going to do exactly that, right? Hence why this is here. This just means like every permutation of 0 and 1 up to that up to length n. And so what we're going to do is at each we're going to just pick a vertex to start off, and we're going to pick a bit uniformly at random, and there's a 50% chance we're going to update it to 0, and 50% chance we're going to update it to 1. So that's our algorithm for how we're going to randomly walk the hypercube. And what we want to find is how long it's going to take before we have seen every single vertex. So we're going to make a coupling. So let's say now we have 2 chains, okay? And in both of them, we're going to pick the same vertex, right? So we condition them. We basically say they're conditional on the same random variable. So they're always going to pick the same bit, right? And they're always going to agree as well on what bit they're going to update it to. So the key thing to note here is that let's say you're doing it on a square, right? And you pick the coordinate 0, 1, and then your random variable says to update it to 1. Well, then both of your chains are now going to agree on that bit, right? And every step after that, they're still going to agree on that bit because they can only ever be updated to the same thing. So basically what we're looking for now is just the probability that given a time t, every single bit has been selected at least once. So we're going to let tau denote the number of steps before every bit has been selected at least once, and a sub I denote the event that the ith bit has not been selected among the first this arbitrary number of steps. Now the thing here is, right, this looks like a really weird number. A lot of these proofs, the way you typically go about them is you just put a placeholder in here, do all the rest of the math, and then work out what you need to put in here such that it actually means something useful. And we'll see why this shows up in a bit. Because then we can say that the probability that sorry, brain. Okay, yeah. The probability that no, yeah. Yeah, so the probability that the number of steps required for every bit to have been selected at least once is greater than this thing is equal to the union of all of these things, right? Which makes sense because you're basically saying that after all these things have occurred, you have selected every bit, right? And this just comes from classic like inclusion exclusion. You can bound it by this sum. And that's quite a common thing you see in these proofs is just like big upper bounds on things because it's too hard to work with these other representations. So because every time you pick a bit, you then no longer care about that bit anymore, you're basically reducing every time you pick a bit, your chance of picking a useful bit in the future decreases by, well, 1 on n, right? So from that, you end up with this sum from the previous equation, which you can bound by this, which results in this. And then what you can basically do, because what we care about, right, for the mixing time is when this d of t here, this means the distance, the total variation distance between the current distribution of the chain and the stationary distribution. And we care about this being less than a quarter or less than epsilon, right? So you basically just sub in d of t equals epsilon, and you arrive at this nice expression here. In other words, we find that the mixing time is polynomial, and specifically it's O of n log n. As for graph coloring, if we remember our rules from before, you pick a vertex at random, pick a color at random, try and update it if it's allowed. So our coupling rule is going to be both chains are going to pick the same vertex and color, and we're going to treat the distance between them as the Hamming distance. In other words, the number of disagreeing vertices. So once again, big thanks to Critter. Here's an example of like two initial colorings, right, for the graphs. So you can pick any two colorings, right? And there's basically a few cases we need to consider. We can consider a good move, right? So a good move, this is the case where it's selected this top right vertex here, and it's updated them both to be green. Now for this one, nothing changed because it was already green. And for this one, it was a valid change, so it did it. And now the distance between these two has decreased by 1. There are also bad moves. A bad move is, for example, in this one, it selects this red vertex and tries to update it to green. Now, these are already the same, right? But if you update it to green in this chain, it's invalid, so it'll just remain red. Whereas this one, it is valid, so it'll remain green. This means that now you basically increase the distance between them by 1. Finally, there are also neutral moves. We don't really care about them. We'll see why. But yeah, you can, in this case, it's picked 2 vertices that were already different, not already different. They were already they were already different. Yeah, and then tried to update them. Both of them failed, right? Because this is invalid, and therefore the distance remains the same. So now we can consider basically all those cases, and basically compute the expected value of the next state given the current state on average, right? Which this part comes from the current state. This part comes from the good moves, right? You're basically saying there's a k minus 2 delta on kn chance of the good move happening. But okay, also something to say. K is the number of colors. Delta is the maximum degree of your vertices. This comes from the fact that there are k minus 2 delta good colors, basically. Not quite. There's a whole. It's very involved. I could go over it, but I think we'll be stuck for time. Yeah, and basically just evaluates to this nice expression here. And then this is where it gets really, really ugly, because now you have to recursively apply this inequality across every single pair of states, right? Very, very involved. You have to basically see some magic exponential thing that you can bound it by this. And then you basically have that so long as k is greater than 4 delta plus 1, then this should rapidly mix. Now, this was a very ugly process, right? And for a long, long time, this was basically what people in the field were stuck with. Yeah, so especially the bit where we had to recursively apply all the couplings, very, very painful. Lots of inequalities of exponentials. There was also a brief period when the main way of analyzing these was with spectral gap analysis, which is basically where you're doing all manner of linear algebra on the transition matrix and trying to show properties through that. This was even more ugly. I have read there are like 30-page proofs that exist for this. And then, anyway, so there was a bit of a dark age in the field. No one really, okay, I said dark age. It was a very new field, so no one really knew what they were doing. But then, in 1997, Bowley and Dyer released a paper describing path coupling. One sec, guys. Okay. So, just a bit more setup before we can get to what path coupling actually is. Start off by defining a pre-metric, which is just a weighted connected undirected graph, right? So you're somehow relating every vertex to every other vertex, right? And then saying, well, not every vertex to every other vertex, but it has to be connected. So there's one component. And then there's also an added requirement on this pre-metric that if there's an edge between 2 vertices, then that has to be the shortest path between them. You can't have any shorter paths that take a different set of edges, basically. And this lets us then we can then basically extend this shortest path metric, which we're going to call small delta, right? And what we can do with this, we will see in a second. So if we can couple any 2 states now in this graph, right, and consider the shortest path between them, which is always going to be some sequence of edges, right? And then we can compose them all as we did just now, right? We're basically just doing the same set of steps that we just did for the coupling argument, except we're generalizing it. So that instead of using that one specific coupling, we're saying, how can we apply this to an entire class of couplings, specifically those where we're considering a distance metric, like a shortest path metric on that particular kind of free metric. And so then we get this wonderful expression where we're basically saying that the expected distance of between, so if we've got our two chains, the expected distance between them after running it for one step, given the current state, is at least less than or equal to the expected value of this big sum, right? Which is basically the how we did before when we recursively applied it to every adjacent coupling, which this expression is the same thing as this right here, because you're saying that by our earlier metric definition, the distance between any two subsequent states in this in this chain must be smaller. And so overall, we arrive at this here, which is actually a very powerful expression, because what it lets us say is that basically the chain will mix in 1 alpha log d time, where I'll get to what d is in a second. But the reason that comes up is because you're effectively saying that you're dividing the distance between them by this amount every time. And the diameter is the longest distance between any two states in the graph. Cool. So now we're going to look at how we can actually apply that to the graph coloring problem. Oh yeah, first off, let me just okay. This is a brief animation of what it shows. Is kind of it just shows two graphs approaching, like running the same chain next to each other, and basically you get to see how long it takes for them to converge, right? So you see that's sort of pretty far apart, and then as the chain is run repeatedly, you eventually get to the point where they just sync up, and then from henceforth they're always going to agree. And so by using a path coupling argument, you're basically taking each step of that, bounding it by some amount, and then recursively applying that bound with that general form from earlier. Cool. So we're going to look at our exact same chain as before, except we're going to couple it slightly differently. The main difference is that now, if we pick, first of all, okay, the first thing we're going to say is that the two chains start in configurations that are exactly one vertex apart, right? So they agree on every color except one. Then, if one of the chains picks if the random variable selects a vertex that is in the neighborhood of that vertex that's the same, then if it also picks the color of the vertex that's different, then the other chain will pick the color of its vertex that's different. And the same thing in the other direction. So basically, yeah, if it tries to update the color and it's not possible for the second graph, then it will pick the first graph's color. And if it picks a color that's not possible for the second graph, then it will pick the first graph's color as well. Yes. Cool. Otherwise, everything is the exact same. Now, you may be wondering why do you have to do it this way? Remember, a condition on our coupling is that they have to be on the exact same state space. If you were to say, for example, if C equals Cx of V, Y also picks Cx of V, and then if C equals Cy of V, then Y also picks Cx of V, you would have that Y would basically only sample one less state, so it wouldn't have the same state space. So in our first case, we have that we pick the vertex as different, in which case the distance between them will decrease with this probability because there are k colors minus delta invalid colors, right, for each vertex adjacent, divided by kn. And then the second case is where we pick something in the neighborhood. This one's a little more complicated. There's a few cases to consider, but the only one we care about is that case earlier, this one here. Because if it picks the second chain's color, then this one will update to the second chain's color, and this one will update to the first chain's color. So they were the same before, but now they've actually changed, and so your distance increases. And that will happen with that probability there. And the other case is invariant. There's no distance change, so we're all good. We then apply our coupling the exact same way as earlier, and we find that the expected distance is less than or equal to this number, which if we look at our earlier expression for, here, right? Our delta of xy was just 1, right? We said that in the, like we specified that at the start of the problem. So our alpha is 1 on kn. And therefore, we can use that expression from earlier to say that the chain mix is in O of kn log n, which is very cool. We've basically just made, we've reduced the bound from before it was 4 delta plus 1. Now it's 2 delta plus 1. So slowly, getting the possible like classes of graphs that we can run this on to be like a bigger and bigger group of graphs. Yeah. So kind of takeaways and stuff, I guess. I just think this is a really pretty demonstration because they've taken something that was so ugly, so difficult to, you just have to kind of sit down and slog it out with all these disgusting inequalities, and generalize it to a point where you basically just show like a few small things and then the math kind of just does it for you. Especially looking compared to like the spectral analysis stuff, this is just so much nicer. And it's kind of awesome that you can just do that. You can take something so general and turn it into, you basically use math as a tool to generalize it even further. Other than that, why, once again, like why kind of do we care about it? There's been a whole lot of research into it recently. Particularly the bound has been reduced to as far as k greater than or equal to 11 on 6 delta. So that's as far as we've got. And there's a big conjecture in the field that it is rapidly mixing for k greater than or equal to d plus 1, which would be huge news because then you're almost at the point where it can deal with like most classes. Like you can find a smaller and smaller coloring, which is useful in a lot of cases where you care about having a smaller coloring. E.g. for timetabling is an example. Where you want to have things overlap. Basically, your timetabling is more efficient the lower the colors you consider are. As for what my group actually did, we basically looked at 2 novel chains. The main kind of interesting one is one where instead of picking the color uniformly at random, you actually weight it based on the frequency that the colors show up already. So the more a color is already in your graph, the less likely it is to pick it. And we sort of conjectured, okay, this is going to do really badly on star graphs because you can, for example, you can 2-color a star graph trivially. You just say middle point is one color, every other point is a different color, and it would always weight the outer colors worse, even though it needs to pick more of them, right? And surprisingly, we ran this several times. It was consistent. This is the mean time to first value coloring on a star graph, this one here. Blue is our novel algorithm and orange is Metropolis, and it performs like significantly better. So a big thing is going to be trying to work out why that is. So nothing's been formally proved. For somewhat obvious reasons, it's very, very, very difficult to do a path coupling argument for this kind of chain because you basically multiply the number of states you have to consider by k. But hopefully we'll get somewhere. Other takeaways, research is fun. I've had a great time doing this. It's been really cool just like diving into stuff without, it's a lot of freedom involved, especially compared to like the rest of university. I kind of wish it was more self-motivated in other classes. I feel like so much stuff is just prescribed and you don't really get to explore stuff yourself. That said, probably not going to do any more algorithms research. That's probably enough for me. A little too abstract. My heart's still with hardware. Yeah, cool. Thank you.
All right, so we have any questions?
Yes. So you said that the field is getting better and they're finding more and more efficient algorithms. At what rate are those filtering into the real world or implementations? Like,
Not really. Well, okay. So the applications of this are actually quite scarce. They're basically only useful in scientific computing. You will not see these in many like actual applications that you're going to use on the day-to-day. My Discord is on. I should turn that off. Damn it. So practically none at all is what I'm going to say. There is also a kind of more general application of this to if you want some like really strangely shaped distribution. This is very useful for doing that because you can. It's quite randomness is a difficult problem for computers to do. You can basically describe this set of like sort of like I guess deterministic steps. In such a way that you can make whatever sort of strange stationary distribution you want. Like I've seen examples where people wanted a like 6-modal distribution for something, and the way they got their computer to do that is to find a Markov chain that mixes to something that looks like that. But yeah, applications, there's basically just that physics thing I mentioned. And in terms of like finding approximation algorithms for like, if you only care about finding a coloring and not like several, there are better ways of doing it than this currently.
Yeah, so there are limited applications, but for those applications, like if it's, physics, let's say NASA's running Ruby, what are the odds that the Ruby version they're using is going to have the faster, the 11/6 version instead of the 4 version? Considering
that paper came out this year, I think very unlikely.
Ruby moves fast, but yeah, that's all from me. Anyone else?
Yeah, so I have a question. You mentioned something about timetabling and like the coloring.
Yes.
So like register allocation in compilers is basically a graph coloring problem.
Yes.
And I was just asking, maybe is there any like applications towards that?
Okay, so it's interesting you mentioned that specific case because my understanding is that give me a second to think. You can also reduce register allocation to 3 satisfiability, which is another NP-complete problem, but is a lot easier for computers to do. In most cases, they can do it like very fast. So this is probably still not the best way of doing register allocation. You'd be better off using whatever 3-sat implementation you have. So yeah.
Yeah. Okay. All right. Is it for everyone? All right. It's good.
Yeah.
All right. Up next, we'll have Evan. So you can come get set up.